Okay, in this video, we are going to try to take a look at the kind of more mathematical side of how we establish the triangle congruence postulates. We looked at it from what I consider an engineering or architectural perspective, where the line segments are kind of like having constraints on them. This one is going to be trying more to demonstrate from a mathematical perspective why these things are and why they work. Remember that they are postulates, so they don't require any kind of proof, but we're still going to try to demonstrate where they come from and how we can be certain that they are correct. So we start with side, side, side. So we're going to put that up here, side, side, side. Side, side, side is basically we know all three side lengths. So I could create that by drawing three separate line segments and then basically taking them and turning them into a triangle. So I could take a black line segment, a green line segment, and a blue line segment. And then I could manipulate those. I'm not changing their length at all, I'm only changing their angles. So this is showing that it's the side lengths that matter, not the angles. And there should be, so notice they don't quite meet there, right? So I'm going to have to find the one configuration where they meet at a point. And there is a better way to do this, which I'll show you in just a second, because this is very tedious, especially with this drawing tool that we have here with the textbook. Okay, so pretty close, almost to getting them touching. Pretty darn close. So that's pretty much our triangle, right? But there's another way that we can do this without having to kind of manipulate and rotate the segments like that. Let's take these same three segment lengths and make them the black one, the green one, and the blue one. But let's see, and we can kind of through our struggles there see that there's only one way to connect those, right? I could get them closer and closer until they finally touched, and then beyond that they would start crossing. So let's do a construction that's going to kind of show how this works. So we're going to construct a segment, it's about or a circle that's the length of the green segment starting from one side. So the thing circles are really good for is I know the radius stays constant. So I know the distance away from this end point is always the green segment. What I don't know when I'm drawing a circle is what angle I'm going to be at. So this represents, as I took that green segment and was kind of turning it, all the positions that it could be in. So the second endpoint of the green segment has to be along this circle. Similarly, if the compass is wide enough, oh, it is good, I can make a segment that represents the blue line. It's not quite flat. Let's see if I can flatten this blue one just a little bit better so I can measure it properly. Maybe that. Good. Okay. So we've got our blue segment measured. We're going to put it here. And then we're going to do another circle of that size. So wherever we end up with those two circles crossing is going to be the only place that we can make our triangle. So is that what our triangle looked like? I don't even remember. So basically the blue segment and the green segment will meet at that point. Yeah, that looks right. So my blue segment will go from an end point to that intersection, and my green point will as well. So something like that makes my triangle. Now notice the circles intersect twice. So they intersect here and they intersect here. But I end up with the exact same triangle, it's just a reflection around the black line. So if I reflect the triangle across the black line, then the two green and blue would intersect over here instead. So this method of construction with two circles and showing that they only intersect in one possible triangle, even though we have two copies of it, kind of proves to us that side, side, side is a thing, and that we only have one possible circle that we can, or one possible triangle that we can make there. So let's clear that one and move on to the next one, which will be side, angle, side. Yeah, side, angle, side. Okay, so side, angle, side starts off kind of similarly. We have a line segment that is our initial side. Then we have an included angle, meaning that I'm going to draw an angle at one of these endpoints, and then our next side length of known, side of known length, so let's get another side of known length here, we'll make that green, is going to be coming off of that angle. So to make an angle of a known measurement, I'm going to use a protractor. I'm going to place it here, and I'm going to set my angle to say, it doesn't really matter, let's set it to like 35 degrees, and draw a ray going off in that direction. So the ray, remember, is no specified length, it's just defining the size of this angle and how open it is. What we want to do then is make this segment follow that ray. So we're going to do that by moving this segment of known length and aligning it with the ray so that it goes right there. So now I have two fixed points. The end point of this is known because we had a known side length for the black segment. The end point of this green one is known because the angle here is set and the length of the green segment is set. So there is only exactly one way I can close this triangle, because between any 2 points, there's only one line connecting them. So I have this point, and there's only one segment that I can draw to complete that. So that's how side, angle, side works, in that we draw the side, have a fixed angle, and then that side, and now we have these 2 points are locked in relative to each other, so we have to close it with that segment. So that's side, angle, side. Next we're going to look at side, side, angle. So side, side, angle is a tricky one because sometimes it works. So let's look at both cases for side, side, angle and see where it works and where it doesn't work. Let's start off with a line segment, like always, because we have side, side, angle, so we'll start with a line segment here. And then we're going to make a second line segment, but we don't know what angle it's at. So we're going to make a circle because we have a line segment of unknown length. But then at one end we also have an angle that we do know. So let's go ahead and draw our circle. We'll make it like that, and we'll make it in purple. Okay, so we have a purple circle. Now at the other end, so we have side, side, right? And then the angle is over here, not the included angle. So the included angle would be over here on this one. That's what we did with side, angle, side. We're defining this other angle at this endpoint. So to do that, we'll use our protractor again, and let's make our angle, I don't know, we can just do 35 again, that's fine. We can be boring and create a ray at 35. So what we end up with is basically a couple of options for what our triangle could look like. So if we extend this ray infinitely, not infinitely, but as far as I can on this picture, it's going to come out like that. So we know that to finish our triangle, we need to connect this end point to a spot where this ray intersects the circle. Unfortunately, though, there's two different options for that. So if I connect to here, then I have formed a triangle that has the correct two side lengths and the correct angle. If I, however, connect over here, I've also done the same thing because these two segments, the green and blue, are the same length if they were drawn to the center correctly. So the green and blue are the same length, so I have this one super skinny triangle and this one great big triangle. So what's happening between those is the angle that I defined, the 35-degree angle, is an acute angle. That means that there's going to be an obtuse angle somewhere, and it could either be the included angle. So here with the blue one, my included angle is bigger than 180 degrees, bigger than 90 degrees, not 180, can't be bigger than 180. Is bigger than 90 degrees. In fact, if I measure it, it looks like it's about 102 degrees. So that obtuse angle is there, but in the green one, the obtuse angle is the other non-included angle. So we had an acute angle for one non-included angle, and then the other one could be, let me line up the 180, the other one could be the obtuse angle. So here, our obtuse angle is about 140 degrees in the little green skinny triangle. So the fact that we don't know where the obtuse angle is kind of the heart of the issue. So let's take a look at a different version of this. We're going to keep the same starting side. We're going to redo this, and we're going to redo the angle. So let's start from here again, and we're going to make our circle, which I'm going to make big. Okay, so we have a circle, and then the circle's not big enough, is it? Let's make our starting line segment a bit shorter in this case. So we're going to redraw our starting segment to be a little shorter just because the limitation of how big the compass can open. So we'll do something like that, and then make sure we drew the circle starting right there. Okay, so now what we're going to do is create that angle we made again here from the other side. So this is our non-included angle. It's not perfectly lined up. There we go. And this time we need to make it 90 or bigger. So when this angle is acute, we end up with two options for what triangle we could end up with. But if it is obtuse, then we're going to end up with no ambiguity. So let's make this 120 degrees and create our ray. And now you'll see that no matter how far I extend the ray, it can only cross the circle once. We can't cross it a second time. So the only way that I can close this triangle and complete it is by going from the center of the circle to that intersection to create that triangle that has the black side length, the green side length, and this known angle of 120 degrees. So as long as this non-included angle, the A part of SSA, is 90 or more, then it is a valid way to determine congruence. But if it's less than 90 degrees, then it's not valid because there's two triangles that we could end up with. Okay, so those are our three side-based ones. Let's take a look at angle-based ones. So the easier one for angles is angle side angle, because we still have a side that's known. So let's go ahead and make this side. And now we're going to have two known angles. So I'm going to start from one side of my segment and make an angle of, say, I don't know, 70 degrees. Really doesn't matter. I'm going to create a ray. And then I'm going to put this other angle, which is also known. And this is going to be, say, 45 degrees. Create a ray. So remember that these rays extend forever and ever. They're infinitely long. So at some point, they will intersect. So if I keep extending them, take this one and go like that. Take this one and go like that. And then adjust them a little bit to be in line. Then we're only ever going to have one way that they can cross. There's one end point which is going to form this triangle. And that's because we knew this, let me just use the pencil. We knew this angle, we knew this side, and we knew this angle. So that means that these two rays are starting from fixed points. We can't move them. And as they go off forever, eventually where they cross is going to be completely dictated. There's no way to change where they cross. So this is angle, side, angle, which I didn't remember to type, but you got it. Okay, and the last one that we can use is angle, angle, side. And this is the hardest one to visualize. So it's also really hard to draw, not on a computer. So I'm gonna make two known angles. Let's go with like 35 degrees, and we'll go with 64 degrees. So it doesn't matter what these angles are, but we have two known angles, and we have one known side, but it's not the side between the two angles. So I'm going to draw this known side. I'm going to use a different color this time. Let's do red. Okay, so we have this side, and we know that it's formed by one of these angles, but not the other. So I can place this angle here, but I'm not going to put this one here, because that would be angle, side, angle, where the side is included. This angle here has to be the other angle over here somewhere, like it's up here somewhere in space. I don't know exactly where. I actually think just looking at the size of these, I'd rather swap them and put this one here. Doesn't matter, I'll end up with the same triangle. Put that one there, and this might not be any better, and put this one somewhere up here. So I know that I need this angle to make a side that runs smoothly into this one. So I'm going to adjust this as much as I can so that these two coincide. It is not behaving. Okay, so that's pretty close to coinciding there. And now what I need to do is basically slide this one away until this ray exactly passes this end point. So to help us do that, let's draw some new, or some extensions for this ray. And for this one. And then adjust this a bit. Okay, so now we have extensions for our ray. And what we want to do, whoops, I missed it. Like I said, this one's tough. Okay, we got our rays. So we have this overlap, right? And see how currently the second ray is cutting through our known side. But we know that we have to get to this end point. So we're going to slide this along and basically telescope it out to where we're keeping these two overlapped, and we slide it back until we just get to the point where that one meets that end point. So this is our triangle. If we keep sliding it out further, then there's a gap there, right? This side of known length is not long enough anymore. So we have to come back to exactly this one spot that perfectly overlaps the two rays and that meets the end point with this other ray. So this is kind of a visual of why there's only one possible triangle here. We can't keep sliding those apart or it would break everything. Okay, so then we know the last one, angle, 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 doesn't give us congruent triangles, but let's take a look at, again, visualizing why that is. So we're going to make three angles. We'll do 20 degree, let's do 30 degrees. Create angle. We'll do 54 degrees. So 30 and 54 is 84, so we have 96 left. 96. So these three angles add up to 180, so they have to form a triangle. But the problem with angle, angle, angle is that they don't just form one triangle, they form an infinite number of triangles. So to see that, we're going to start off what we did last time, which was overlapping these rays. Now I'm questioning, did I make this right? Maybe. Yeah, that looks about right. Okay, so we overlap the rays, and we do create a triangle with those three angles. The problem with this is if we do what we did in the last one and slide these away, so slide this back along that same path, and then also slide this one back along that path, I would need to extend that, but since we don't have any given side lengths, I can extend this to make those meet again, and we can end up with an infinite series of similar triangles. So I could even make a really, really small one if I bring these close together. So I can make any number of similar triangles that have all three angles the same, but the sides are not the same, they're just proportional. So this was kind of just a view in geometry with the geometry tools of how we can construct, not just construct, I guess draw, since we're using measuring tools, how we can draw these different scenarios to kind of understand the triangle congruence postulates.